The product rule is one of the first differentiation rules that starts to get ugly in terms of working out all of the algebra. And before we do any of that work, I'd like to skip most of it by just using some concepts here. So I'm going to draw this out. And I'm going to use an analogy here, but let's say I have a function f of x, which I'm just going to label as u, so I don't have to write this every time. And I have a g of x, which I'm going to label as v, so I don't have to label that every time. And I'm going to use this to find some function p, which is also dependent on x because it's f of x times g of x. Okay, now we have rules like the power rule. If I have e to the x plus x cubed, when I want to find the derivative, we can do them separately. But when they're multiplied, it's not so easy. Because if you use this as an analogy, here's a rectangle whose width and height are u and v. If I change x, it's going to affect both of these, not just one at a time. So we can't separate these quite as easily. And if I change the height v, well, that height difference would be a delta v. And this width would still be u, so the area here would be u times delta v. And you know what? Let's make some space here because I'm going to write something. The area here would be a delta u and a new height v, so this would be a v times delta u. And this area in the middle would be delta u and delta v. And you may remember, let's fill this in a little, you may remember that when we differentiate, we want to be talking about the rate of change. So the original area uv, maybe we already know. But what we want to find out is when we change x, how fast does this little thin, infinitely small thin slice change, and how much does this infinitely thin slice change? And then how does that affect everything? Well, when we were finding limits, you might remember that if you did like an x cubed over like a 2x, as x approaches infinity, the only thing that really matters is the highest degree. Infinity cubed is literally infinitely more important than infinity. And that might sound funny, but in this case, an infinitely thin line and an infinitely thin line are infinitely more important than infinitely small and infinitely small squared, right? So I want you to look at this and understand they're going to tell you the rate of change for this. So you can remember that in kind of a visual way. But here's where the algebra is we're going to skip right over all the deriving. You can do that on your own time if you hate yourself as much as you want. I fully support you trying to learn that if you want to be a real mathematician. But I want to apply mathematics. And in my case, I'm going to put it this way. I'm going to say p of x is equal to f of x times g of x. And I'll give you an example, like maybe it's e to the x times sine of x. You're doing something like this work, right? Let's check, make sure we're recording, because I've done this twice already and it went very poorly. So where's my... I'm going to rename this now as u times v. Okay, and I'm just going to call this p. They're all dependent on x. You understand this now, so I can leave that part out. Okay, and I'm going to say if I want p prime, which is equal to the derivative of u times v, you are going to get those two sections, which is u prime, that's a terrible u prime v plus v prime u. And I think we call it this specifically because it rolls off the tongue so easily. For two multiplied items that are both dependent on x together, u prime v plus v prime u gives you the derivative. So I'm going to give you an example. I'm going to tell you a secret that the derivative of sine of x, which you probably haven't seen before, is cosine of x. Just accept that as true for this example, okay? And I'm going to give you a formula. Like, let's say I give you p of x equals e to the x sine of x. You see that these are multiplied? They can't be done separately on their own, like with the power rule. That only works if things are multiplied together. If they are simple addition. like they're separated by a subtraction or an addition, but these are multiplied. These are a combined function in that way. So we are going to write out what each of these two functions are. The first one is e to the x, and the second one is sine of x. And then when I find u prime, well, we know the power rule, or the e to the x rule, is itself, and v prime, I just told you, is cosine of x. So if I want to find p prime, I would simply follow the rules. U prime v, which is e to the x, there's my u prime, and my v is the original, plus v prime, which is cosine of x, times u. That's e to the x. And if you want to get funny with it, you can do e to the x and sine of x plus cosine of x. Well, one of the cool things you can see here is actually this original function, e to the x sine of the x, sine x, is right here. So you could even write that p prime is equal to p plus this here, e to the x cosine x. Isn't that strange? So we're getting into a world that's going to come a few math classes later. But here you have in the same equation a function and its own derivative plus some tail stuff here. It gets pretty wild. Let's do some example problems for this chapter over on the problem playlist and apply this a bit though. And what you need to remember is that for multiplied functions that both depend on x, their derivative is u prime v plus v prime u.